And it doesn't look like I have any obvious mistakes in there, so run this. Yeah.
Can I see your Bemidji data table? Did you add that info for me?
Probably. And so yeah, when you're doing the select into statement, all you have to do is select the impno column in there as well. Maybe I didn't do that before, but here is my example query that led me to that eventually.
Okay.
So I may not have said that in class, you're right.
I probably forgot.
Any other questions on homework 5 due, sometime this weekend? I would prefer if it's due today, but I'll wait until after Sunday to actually grade them and count things late. I just want to make sure that we get this done as soon as possible so that we have time for another one before Thanksgiving break. I was going to give you that new one today, but I'm not going to have time for that. I'll give it to you on Monday, probably. That still gives you a week before Thanksgiving break. I do not want to ruin your Thanksgiving break by having you work on one of my assignments over it. No other question? No other confusion? Devin, that
Yes.
word on the whiteboard, how do you pronounce that?
Oh no. It feels like a trap.
Yeah.
Aunt?
It absolutely is. You freaking Minnesotans. that clearly is pronounced ant. Come on.
I suppose? Well,
Now, I expected everyone in my previous class to pronounce that ant, and most of them pronounced it aunt. So I'm blaming it on northern Minnesota.
it's that capital U. That
Yep.
really makes me feel like I should lean into it.
All right, well, let me, so I don't know how many of you have built your way up to the 10-point prediction model, but probably Tyler, did your SQL look something like this when you wanted to get 11 consecutive U's and 11 consecutive V's? Basically, you follow the same pattern that you had when you were joining 3 tables together. You just keep on adding tables. And since the instructions in the homework are only predict the wind values between July 2nd up to July 4th, because I want to exclude that July 4th windstorm from your data, then from your graph, I'm just not returning all of the results, but only the July 2nd through July 3rd results. And this is the biggest model I have you use. I think, historically, should I tell you what to expect? Is that going to contaminate your results? But generally, the more data that you use to make a prediction, you expect the better the result will be. So I expect RMSEs to go down as we're putting more data into the prediction. Although, frankly, I don't really trust wind data from 10 time units ago, but for some reason it just seems to work out. The more data you use in your prediction, the lower the RMSE. So it's not going to be 100% the case, but that's why I'm having you build a table of my U RMSE for 3 was this, and for 5 was this, and for 10 was this, and for 1, the naive model was this. And you can put the naive model as your first row if you want. That would make sense numerically. But I just want RMSE models or RMSE values for your U models and your V models all in the table so we can compare them next to each other and see which is the one best model to rule them all, prediction-wise, for the next time unit of data. Is more data always better, or are there exceptions? All right, so that's pretty much the main idea of homework 5. I want to start talking about homework 6, which I'm going to try to assign to you on Monday. And the unifying idea behind this, I'm going to bring it back to wind, but I'm going to use a bear weighing scenario to illustrate how to build a different model that uses more than just one data value. Because up to now, we're really just predicting U values of the wind using prior U values. But I'm thinking, since the wind is actually composed of both U's and V's, does it make sense to anyone to try to use also some prior V's to predict the U? Would that make sense to you, Tyler?
Makes sense.
If one time unit ago the wind was blowing this far in the in the V direction and this strong in the U direction, and then one time unit later this is a little bit longer and this is a little bit shorter, maybe is the V stealing energy from the U, and so maybe can we say, well, if U has been getting smaller over the past few hours and V has been getting longer, maybe it makes sense to use U values to predict V values for the next time unit, and the same, use prior V values to predict U values. And so far I haven't been asking you to do that. And so now I'm going to be expanding my models to say, use whatever data you have and join those tables to each other so you get historical data, a series of historical values, and see if homework 5 said more data gives you better results, let's get more data going. It is true, it's November. Bear tranking season is coming. So what we've seen so far is what the statisticians would say is a single variable regression type prediction model, where I'm essentially trying to use a series of historical values in order to get an M and a B that I can use in a Y equals mx plus B formula in order to figure out the data for time unit 4 if I'm using 3 prior values to predict the next value. And this is how we learned that formula in math class, but if you were learning this in a statistics class, you probably saw it in this form. It's exactly the same thing. They're just saying a variable with a caret above it is just the predicted Y, or it basically means predicted Y. Predicted Y is equal to this beta coefficient times X plus this beta coefficient. And so basically, statisticians name all of their coefficients Greek letter B. And if you have more than just one input into your prediction model, then you're going to have a whole sequence of beta 0, beta 1, beta 2, beta 3 coefficients multiplied to them. That's just going to be a multilinear regression model, and that's what I'm building up to. And so we've been using SQL to extract data from our database such that we can build this homework 5 series of models, these linear time series models. But basically, they're just in service of a Y equals mx plus b predictor model. And part of what I hope you're going to discover in homework 5 is that these predictions can be limited. Right now, our predictions are limited just by the fact that we're just using U's to predict U's, whereas we have a whole series of V's that we could be using, but I don't see how I can make those V's fit into a Y equals mx plus b formula. That's why we're not using them yet. I'm going to abandon Y equals mx plus b for homework 6 and do something more statistically common. Basically, have Excel build an ANOVA model for you. And I'm not going to explain the details of ANOVA. I'm just going to say Excel is going to do it for you, and it's going to magically give you numbers that make sense for your coefficients. All right. But yeah, it would be nice if we have different types of of values. I mean, we also have humidity values from our humidity sensors. We've got barometric pressure values that we could be using. And again, I can't shoehorn those into my y equals mx plus b, but I would really like to use a model that could integrate different values from different places. Some of them might be related to each other, some of them might not. I mean, I think in our heads, we build models like this all the time. If, for example, we had a weatherman on TV tell us what the temperature was in Grand Forks, and another weatherman told us what the temperature was in Minneapolis, St. Paul, and we were sitting here in Bemidji, we might say, given those two pieces of information, maybe I just average those two, and that's maybe an okay guess approximation for what the temperature is in Bemidji. And so yeah, that's an example of using two different types of values and putting them together in some way that gives us an okay approximation for what we really want to know. And so the statisticians would define a multiple regression model with k different inputs, k different variables, as something like this. We just have k plus 1 beta values because the 0th beta value, the 0th coefficient, is going to be the y-intercept, the b in y equals mx plus b. So far, we have actually been using this model. It's just we've been using a limited version of that model. There's the y equals mx plus b model. If we were to add a single new variable to this model, that would give us a three-dimensional model rather than a two-dimensional model. And so 3 dimensions is where it is the last graph that we can make to realistically represent our situation in Microsoft Excel. And so I'm going to move to a system where we're using like 15 or 20 models. We're not going to be able to make graphs of those situations, but we will be able to make create columns of the actual value we're trying to predict, and then the prediction that we came up with, and then we can build our RMSE off of that. But we're not going to necessarily have we can still graph those two series together, and that's basically what we've been graphing so far. So I guess multiple variables, multiple inputs to our models aren't going to change what our graphs look like all that much. But if we were trying to fit a linear object to a cloud of points in a three-dimensional space, much like the one that we're living in and moving through right now, we would have all of these points floating in mid-air in this classroom, and then we're not passing a line through that cloud of points. We're passing I don't know, maybe it's a sheet of paper, but it's got to be a straight sheet of paper. Maybe what I'm really talking about is I'm trying to pass a sheet of sheet metal, and it goes through that cloud of points, and it passes as close as possible to all of those points. So this figure is just showing that we're measuring the distance from these points floating in midair to the closest point on that sheet of sheet metal. And when we sum all that up, it will be guaranteed the minimum distance between all of those points in that sheet metal, because the model figures out the exact slope of that sheet metal that it needs to be in that position, that the y-intercept and z-intercept and all of that. And so our linear models guarantee the best fit for linear objects. I guess the problem is the thing that I'm asking you guys to predict, Tyler brought up a little bit earlier, is that the wind speed is not linear. Wind speed, if we were to graph it, it actually is driven a lot by the rotation of the Earth, the rotation of a circular object, and I'm oversimplifying a little bit here when I say this, but circular objects rotating, powering things, tend to make graphs that look like this. And so you can see right here, when I'm building a 3-point model to predict the fourth point, I'm using a value from here, and a value from here, and a value from here, and I'm going to try to predict a value from here. And you know, on this part of the sine or cosine curve, that's doing fine. But if I were using a value from here, and a value from here, and a value from here, and I pass a line through that, I'm going to guess that value as my prediction, when actually on the sine curve, probably better, that is the value that I would have ended up with. And so a linear model works sometimes pretty well with wind, and then sometimes pretty poorly with wind, because wind actually moves in that sinusoidal pattern. Because a lot of what the wind is doing is caused by the earth spinning underneath it and giving it power. And also, depending on where you are in latitudes, wind sort of moves north-south circles and things around the equator. And so there's a whole lot of things affecting the wind. It's not just what it was previously doing an hour ago or a time unit ago. All right, so anyway. This is all what's driving my desire to use different data values that I just happen to have available to me. I know I, at least for winds, have barometric pressure and humidity. I don't know if humidity levels affect the wind, but let's see, let's find out. I'm pretty sure barometric pressures have some predictive ability, but how much? I don't know. Let's find out. Okay, let me go back to my bear tranquilizing example. So when I go out into the Minnesota outback over Thanksgiving break with my bear tranquilizing gun, I have a problem. And the problem is, when I'm way out by, I don't know, International Falls in the middle of a forest, and I shoot a bear and then run up a tree to wait for that bear to fall asleep so I can come down. What I'm really interested in is weighing that bear, right? I'm building a data sheet of bear weights. And the thing is, I can't lug an industrial quality animal weighing scale out into the wilderness, and once I've got a sleeping bear on my hands, I also can't drag that bear back to town to get it weighed at the wildlife station. And so, what I do have, what I can carry with me, is a tape measure. And I know that if I'm going to ask a computer to help me with this problem, computers really prefer having values represented to them in numbers, and a tape measure is going to give me a whole bunch of numbers that I can use. And plus, I've got a couple of buddies over in International Falls at the wildlife weighing scale place that are weighing the deer and the bear that come out of the forest with the hunters. And so they are collecting, when they're weighing those bears, they're also taking all the same measurements that I'm taking out in the forest. So I do have a set of data that I can feed through a model, and hopefully it will give me some coefficients that I can use when I'm out in the forest and I'm just taking these measurements. That's my idea, that's my plan. And you know, it has worked well enough. I just need a computer to do the algorithming for me because the math is a little complicated. So, okay. I've got these measurements taken from a few zoo animals and from bears harvested out of the forest. And I would like to be able to take all of this data and put it together to weigh my bear, much like I would like to be able to take all of this data that I have on barometric pressure and humidity and V's and put it all together to predict wind U's. So it's the same idea. I'm just going to illustrate it here with bear data, and then you should be able to do the same thing on your own with wind data that was collected into a table that was joined to itself multiple times. Because maybe what the wind was doing 3 hours ago is more relevant, since the wind goes in sinusoidal cycles, to what the wind will be doing 1 time unit from now, than what the wind is actually doing now. Maybe if I know the period of that sine function, I just look at every period time units historically, and those will actually be better than just looking at the last 3 time units historically. I don't know. But Excel is going to come to the rescue, as it always does. The best computer program in the world, Tyler. In the world. You can do anything you want with Excel. So Excel does have the capability of putting together a multivariable linear model for me. The only thing I need to have installed on my computer is the data analysis add-in. Who has the data analysis add-in installed in their Excel on their laptops? No add-ins at all? You call yourself computer science majors? It really is hidden away. But let me show you where it is. You've all got it. You just don't have it turned on.
I've got Minitab in ours.
I don't even want to talk about Minitab, but it's probably better than Excel's ANOVA. All right, where am I? I've got my bear data here, but let me ignore that for the moment. Right now I'm in my data ribbon here, and I've got a whole bunch of useful stuff, but none of them say data analysis add-in or anything, or even data analysis. And so to turn that functionality on, I'm going to go to the File menu, and I'm going to go down to Options. I click on Options, it opens up this dialog here. I'm going to ignore everything. Actually, I'm going to go to the Add-ins section, because I'm looking for my data analysis add-in. I'm going to ignore everything up here, because what I really care about is this drop-down box here. I want to see all of the Excel add-ins that came onto my laptop when Excel was installed. I'm just going to click this Go button here. I don't need to change anything. And it's going to show me a list of available add-ins. And maybe that's hard to read because it's tiny little text, but I've got Analysis Toolpack up here, and then Analysis Toolpack VBA, and then some other stuff that I don't care about. I want Analysis Toolpack. It's generally this first one. You don't want the VBA version. We're not going to implement this solution in Visual Basic. But go for the Analysis Toolpack, and that will add an extra button to that data ribbon. You can only see it when you've selected the data ribbon. So if you're at the home ribbon or the insert ribbon or whatever, you're not going to see it. But OK, when I click OK, I'm going to see a new button appear on the ribbon right about here, as far to the right as possible. Hey, did you see that happen? Data analysis, that's what I want. Once you have that, now you have something that can build you statistical models for a whole bunch of different things, a lot like Minitab, probably. And it can use data to build those models that is already in your Excel spreadsheet, which is what I'm shooting for here. Okay. So remember, my task. I'm out in the wilderness. I'm looking at these bears, and I'm making an estimate for how old they are, how many months old they are. I write that down in the first column. I write down a number for gender. So males are 1s, or females are 2s. Everything has to be represented as a number. Head length. I just take out my tape measure and measure how long their heads are, how wide their heads are, head width. I guess I'm figuring out the age of a bear in total months. Maybe this is the month in which I took the measurement. That might be the time of year. And so their actual age in months, I guess. Their neck width, I guess. The measurement around their neck, their body length, the width of their chests, and these are the weight values that I got from my buddies in town who actually had access to the weight of the animal that they were weighing. And so they took all of those measurements, and then that is the data that I have. I basically want to use all of the prior columns and find good coefficients for them that contribute to coming up with a good guess for the weight of the animal that I've just taken the measurements on, is the main idea. How does that sound? All right, I actually just stole this data out of a statistics book, but, and so I'm a little confused about what some of these columns mean, but I'm gonna go with my definitions here. All right, so how do I use data analysis to get that information? I'm gonna click on that button. It's gonna open up a not very readable form, but it's got a whole bunch of models here. And for some reason, it always pre-selects moving average for you, which is not what I want. I want a regression model. I'm gonna choose regression out of this list, and then click OK. Every other model is a model that you would talk about in statistics class. I never understood anything that was going on in that class. Now I've got a just as unreadable form that's asking me what y values do you want to predict and what x values do you want to use to predict them. Those are those two first buttons. And so I know what I want to predict. I want to predict the weight column. So that's going to be the one thing I'm trying to predict. And just to make the output make sense, I'm going to include the column title in there. And then what are the columns that you're going to use? What are the values you're going to use to predict your x values, to predict your y values? I'm just going to select everything else, including the column titles. And since I selected the column titles, I'm going to check the labels box because it's asking, hey, is your first row just the column titles? Shall I use those as the labels? And I'm saying yes. So by default, it's going to print all of its output results in a new worksheet, which is fine with me. It's allowing me to give a name to that worksheet. Otherwise, it'll just name it sheet 1, and so that's fine with me. I'm not original enough to come up with a name at this point. The only other thing I usually check here is this residuals button. Residuals is just a fancy statistical term for error. How far off from the truth is your model's value? And I just want a column of errors because you saw what I did with my column of errors in homework 5. I squared them all, I figured out the mean square error, and then I could figure out the root mean square error is like the common yardstick that we use for all models to measure their accuracy. So that's why I want a bunch of residuals, so I don't have to do the work to come up with those myself. Excel will do some of that work for me, and then I can get my RMSE from there. I'm going to click OK. It's going to create a new sheet. I guess sheet 4 is what it's called. And so I'm going to explain this stuff here probably a little bit later. This stuff, by the way, this is gold. This is the best information you will ever see coming out of any college statistics or data mining class. I'm using multiple x's to predict my y, and so really the value that I want to look at in this overall result table here is called adjusted R square. So it's just figuring out, I think this model is like 93.8% as good as a perfect model. And so having a high value is good, and usually that value is going to be between 0 and 1. Actually, all valid values are going to be somewhere between -1 and +1, but generally, we always get positive values here, and the higher the better. So if I'd gotten a 0.67 value here, then, you know, as long as it's bigger than 50%, I'll accept it, but 0.67 is kind of lame.
What does it mean when it's negative?
It means the higher your inputs go, the lower your result go. It just means that it's I forget the mathematical term for that. They're not positively correlated, they're negatively correlated. It doesn't mean a bad thing. Really, what we should care about is the absolute value of that value, and the bigger the value that absolute value is, the further away it is from 0, the better your model is overall. It would just mean that your model, your inputs are not positively linearly correlated with your results if it were negative. But it doesn't mean that it's a terrible model. It's only saying you have a terrible model if that value is close to 0. So anyway, that's the overall measure of our model that's not an RMSE. The real gold is right here in this coefficients column here. This is telling me these are all of your inputs. I'm using all of the labels that you selected. Plus, I'm showing you the y-intercept. The y-intercept is a value that just balances out whatever imbalances the other inputs have caused in your model. The intercept is the one perfect number that kind of balances out whatever nonsense is going on with those inputs. And so when we're rating the goodness of all of these contributors, intercept is usually one of the best, just because of its balancing role. But what this table is saying is, if you create a linear model that takes the value of your chest measurement and multiplies it by 9.5, and then adds to that your length measurement times 0.42, and then neck times 5.18, plus age times 0.5, plus head width times negative 0.7, plus head length times negative 8.2, plus gender, 1 or 2, remember, times negative 12.7, plus month times negative 1.9, plus a negative 166.554, then the weight of your bear will be the sum of all of those things. So this magically just gives you the best possible coefficients for that sheet of sheet metal passing through the 8-dimensional space of all of these measurements and the bear weight that we're trying to target along the vertical axis. If I'm trying to express this 8-dimensional problem in 3-dimensional terms. But that is not all. There is a further piece of gold here in this table. Who in this class has taken a statistics class? You're all sort of forced to take statistics, right? You've probably all kind of seen a table like this already. Did you all at least talk about the ANOVA model? And so you probably realize that there's another great column in here. Do you guys remember what t-statistics are?
And the p-value as well.
Yes.
With it.
The twos, I mean, I think the coefficients column is the most important column in this table. Laura, you took a statistics class, right?
Back in cities, yeah.
Yeah. Did you get a table of results like this? Assigning coefficients to all of your inputs?
I don't think we used, I think we used like Pearson on Excel. It was like a
Yeah.
Excel.
Okay, Pearson makes me think p-value, actually. I think p-value, the p is short for Pearson. But yeah, the ANOVA model, the linear regression model, tries to give us coefficients for here, but it also gives us approximations for how good those coefficients are, and those approximations come out in these values. The t-statistic column is pretty much the same as the p-value column. It just represents its data in completely the opposite way. And I always forget, are big magnitudes better or small magnitudes better? Because one of these columns likes big magnitudes better, the other column likes small magnitudes better. I always forget what it is, no matter how many times I read it in a book or I hear it in class. And so the way that I can remember that to myself is I remember that the intercept is usually the best coefficient out of this entire table. And so if that is the highest magnitude value in the t-statistic, that is absolute value, ignore the sign. If 3.6 is one of the biggest values here, and the only value bigger than 3.6 is this 6.4 here, that means that big magnitudes are better in the t-statistic column. And if I look in the p-value column, if the intercept value is one of the smallest magnitudes, the values closest to 0 for this Pearson coefficient, and so I'm looking down all of these numbers here, and this is smaller than all of these numbers, except for this number, which has 8 zeros in front of the 7, but after the decimal. So yeah, this apparently is even better in Excel's ANOVA estimation than the intercept. But basically, the intercept is a better quality estimate than any of these other coefficients. Tyler, what did you have to
I've
add?
just been dying to say that.
Yeah.
You want to throw out, or for p-value specifically, you want to throw out anything that's larger than 0.05, because that cares about the confidence interval. Basically, if it's less than 0.05, it means it's very unlikely to be occurring by chance, so it's actually useful. Everything greater, you want to throw out one by one.
Yeah, so what you're saying is p-values just use the very smallest ones, hopefully less than 0.05. Okay, Tyler, this bear weighing project is very important to me. What if none of my p-values are less than 0.05? Are you telling me I can't use any of these as predictors? But these are all I have, Tyler. These are the only data points I have. So I would modify your statement to say, use the 3 lowest p-values. I mean, use what you've got. But yeah, Tyler is right. If I have, if all of these ended up being 0.000 something, that would be super awesome. That means they're all incredibly relevant to my problem. But the further away they are from 0 in the p-value, or the closer they are to 0 in the t-statistic column, then, the less helpful they're going to be. But choose the 2 or 3 variables that are the most helpful. And intercept doesn't count, because intercept is always going to be added in after you select the variables that you're actually going to track. So, like I said, if I want to use all data available to me, I would just multiply these coefficients times these values and then add this intercept, and it would give me a pretty good guess as to what the weight of my bear is. And now I'm going to look down a little further down to see my table of errors, which is called my table of residuals. And I might as well make this a little bit bigger. So this is telling me for I think I had 50 data points or so. This is telling me that for my first data point, the actual answer was it's not telling me what the actual answer was. It's telling me what the predicted answer was, and it's telling me that I was off by 4.47. And so let me actually look at my table. And so I was trying to predict 80, and then I underestimated that value by 4.47 units when I guessed 75. I mean, 75 is pretty close. It rounds up to 80, but not all of these values are going to be that close. But that's what this is telling us here. If you use all of these variable values, this is how close you're going to be, and then I can just use all of these values to figure out what the RMSE is for my model that uses all available data, and it will give me a result. But now something that Tyler said is starting to work at me here. Maybe if there is a variable in there that's not particularly predictive, maybe including it in my model is doing more harm than good. Maybe it's sending my model in a bad direction, whereas if I wasn't sending it in a bad direction in the first place, maybe my RMSE would be better. Maybe Tyler's right. Maybe I should just focus on, the smallest 3 to 5 values, or any value that's less than 0.05 in the p-value column. So, I mean, I'm definitely, I can't explicitly choose intercept, I guess, but I'm just going to highlight the columns that I care about. And so let's make that guy yellow, and we're definitely making that guy yellow. And according to Tyler's definition, there's only 2 variables in here that are worth a damn for prediction. but you know, neck seems pretty close to 0.05. I'm gonna add that in just for funsies. And if I were trying to limit the size of my model to only the most relevant predictors, maybe I would just build a 3-item model. But what I love about this process is before I had no idea which of these 8 variables would be most useful to me. And Excel is sending me off in a pretty good direction. It's saying ignore these 5, use these 3, and see how that works for you. So that's what? Age and neck and chest. Let me see if I can, really I need to come up with RMSEs to do comparison, but I don't have time for that. What did I say? Age and neck and chest. And so I am just going to make another copy of these 2 columns, Control C, Control V, and then I'm going to take chest and then my Y, Control C, Control V, and now I'm going to ask again, hey, analyze this data for me, build me a regression. I want to predict not the I column this time, I want to predict the U column. And I want to predict it using the R column through the T column. Again, I want to use labels. I want this in a completely new worksheet ply, and I want to see my errors. So that's all pre-selected since I did that before. Now I've got a sheet 5, and the first thing I'm going to look at is this adjusted R squared value. It's 93.8 here. What was it before? It was still, okay, so in terms of adjusted R, my model isn't hugely better. I'm going to look at these coefficients that the previous model gave me, 0.53 for age, 5 for neck, and about 10 for chest. And how did those things change? Again, let me make the numbers just a little bit bigger here. And so now that the numbers have changed a little bit, 0.37 for age, about 5 for neck, and a little bit lower than previously for chest. And then to balance out these 3 variables, now the intercept is -248. What are my p-values looking like? Traditionally, intercept is the best p-value, but again, chest is still the best predictor. Neck is still a great predictor, less than Tyler's 0.05 threshold, and age has become a pretty good predictor. And so I think when age was included with those other guys that were sending the model off in the wrong direction, they sort of polluted age's goodness. Maybe I could have taken the lowest 5, and some of them would have been revealed as pretty good in this model. But I would much rather use a model with few inputs, but good inputs, than use a model with all of the inputs that I have, because some of those inputs may actually be doing more harm than good. So what homework 6 is going to be about is not about weighing bears at all. That is a ridiculous scenario. Who goes around trying to weigh bears, Tyler?
Only crazy people.
Only nutballs. No. What I want to do is gather together U's and V's and get U1 and U2 and U3 and U4 and U5 and V1 and V2 and V3 and V4 and V5, and so all right there I've got 10 columns, but I also want barometric pressure, P1 and P2 and P3 and P4 and P5, and humidity, H1 and H2 and H3 and H4 and H5, and I want to use these 20 columns and to predict the next U, and those same 20 columns to predict the next V, but actually, if I can use less than 20 columns for each of those models, I think that would be great, and Excel is going to tell me which of those 20 columns I should use. Choose the best 5 columns for each model, and you're going to find that, some columns are better for predicting U's than for V's. You're going to find that some historical V's are pretty good for predicting U's, which we weren't able to discover in homework 5. We were just using U's to predict U's, but this model is going to tell us which V's are probably going to contribute the most and the best towards a good U approximation or a V approximation. So that's what the idea of homework 6 is going to be, is to use this data analysis tool to figure out of all of the historical data that you could feed into this model, make it as small as possible and just feed in only the best available data to the model that's predicting the thing that you're trying to predict. And those inputs are going to be different based on what you're trying to predict. And I really have a lot of hope for the barometric pressure input. And historically, that has never really even factored in. It's never been one of the best 5 inputs, and that's just really surprising to me. You can't use barometric pressure to predict the wind, Tyler? I mean, I guess what we're really predicting is wind direction, right? U is blowing in the south, or east or west, and V is blowing south and north, and barometric pressure is really just talking about magnitude. I bet if we were predicting the speed of the wind, not in a particular direction, but just overall speed in any direction, maybe barometric pressure would be more important. But when I'm just trying to predict one component or the other, then that really drops pressure in importance, I guess. I mean, I'm no weatherman. I'm just using Excel to pretend like I am. Any questions? That all makes sense? Do you see the shape of the assignment coming up? So again, try to complete homework 5 as close to tonight as possible. I mean, ruin your weekend if you want, but I would stay up until 3 a.m. tonight to finish the whole thing tonight so you can, enjoy your awake time during the weekend. Because on Monday, I'm going to drop a approximately same size assignment on you. Do 1 week from Monday. I'm going to try to give you 7 actual days to work on it on the next one this time. But you'll turn that in just before Thanksgiving, so I can ruin my Thanksgiving break correcting your reports, or grading your reports. All right, thank you very much, everybody. Have a good weekend. I will see you back here on Monday.